Okay. Hello all, welcome to this quick video where we look at some basic CAS skills that hopefully we have down pat going into the upcoming exams. Just going to go over a couple basic algebraic tools that we can use on the CAS that we shouldn't forget about that can make our life much easier, and then we're going to look at a bunch of differentiation tools or calculus tools in the CAS. So let's get right into it. As always, number one rule with CAS work is we always define our functions. If we're given a function, let's define it. Unless it's part of a multiple choice question, we are likely going to need to use it once and more than once. So let's define it. It's going to save us time in the long run. So as always, it's menu 1 to define. Otherwise, you can also use, the other way would be to whatever we want to define the function as is control and then the key to the right of the number 9. You can press that. It has the 2 dots and equal sign that also acts as define, but most of the time we're used to menu 1 define, and we're going to define f of x as equal to, and for this case we're just going to start with a simple parabola to do some work with. So we've defined it. As always, a handy thing with defining is that we can straight away, to get a sense of the problem, is we can add a new page and we can graph it. So straight away we can graph f of x, and there we go. We've got a bit of a sense of what's going on. How this may relate to an applied problem, that's up to a bit of interpretation, but at least this gives us a bit of insight straight away. The other function we're going to work with, if I go back to my other page, is we're going to define g of x as equal to, this is going to be sine 2x plus 0.5, and we've defined that. Go and graph that as well. We can press tab to get up our options of our function. So let's graph g of x, and we have g of x in there as well, so a nice circular function. If I drag this along, this brings us to rule number 2 that I always say, is that if we're going to define a function, we should try and define it with a domain. So let's go back to our f of x. What happens if we're given a domain in the question? Well, it's really easy, we just use that domain. But what if we're not given a domain? Well, this takes a little bit of interpretation. There's generally hints in the question. So if it's talking about the tide, where x is the time or something like that, time after midday, we're never ever going to deal with negative time. So you can always set your domain as greater than 0. And then where's your maximum up to? Well, it might be, this function is the time showing the tide height over the time of 24 hours. Well, or over 2 days or something. So you look at it and you need to interpret and go, okay, what's a reasonable domain for this problem? Even if it's not exactly 100% accurate, if you can make at least a rough guess, then that's better than nothing, and I'll show you why in a minute. So we're going to define this, and I'll show you how. So it's control and then the equal sign, and we need to use the vertical line called bash. So we use that, and then we just put in our domain. So we are going to have 0, control equals, to bring up our inequality symbols, x, and we might go to less than or greater than, less than or equal to 10. There we go, we've defined. And if we go back to our graphing, we can see it has automatically updated. So that's pretty handy. So that's our 2 rules. Define a function, and number 2 is include a domain where possible, even if it's a rough estimate, because it'll avoid issues later on. Right, so a couple basic tools. Solve. The best one that we can use in algebra is, having looked through these are all tools that we shouldn't forget we have. Solve, factor, and expand. 3 really handy tools. Even solve system equations that may come up in a tech active exam. Being able to do this quickly using your CAS rather than grinding through it by hand, especially factorizing. If you're giving a cubic and you've got to factorize, don't try and go and do long division or guessing all the factors and using null factor form. Just factorize it using your CAS. But just quickly, to give a demonstration, let's go f of x is equal to 2. So I'm taking that original function I want to find out, solve it for when f of x is equal to 2, and remember with the solve we need to say what variable we're solving for, so comma, and in our case our function has x in it, so we need to solve for x. Hit enter and it gives me the answer. So nice and handy. Same thing for factorizing menu, algebra, factor. Let's just factorize f of x. And it looks like we haven't. Actually, let's copy this without the domain, and let's now try and factorize it. No, okay, so it has no real factors. I'm guessing that's what's coming up. That's what's showing us. Let's try something that I know has factors. Give me 1 second. I'm just making up a problem that I know has nice integer solutions. Okay, let's define h of x is equal to x to the 2 plus 7x plus 10. Okay, now let's factor h of x. There we go. Okay. So what was happening with f of x is it didn't have nice integer factors, but h of x had factorized it for us nice and easy. Let me go back and redefine f of x with my domain, just for useful. So what we've still got our two functions. F of x is our parabola with our domain, and then we also, just so you're aware, we have g of x, which is our circular function. We can see them graphed there. So where from here? The only other tool would be expand, which just does what it says, is that it'll expand a function, which can be handy if maybe you're given a function in a non-standard form and you want to expand it out before you could use the factor tool to factorize it, normally maybe to find the intercepts or something like that. But that's the basic CAS tools, the basic algebraic tools. Let's start looking at differentiation, and especially in relation to circular functions, and something to be aware of. Or this actually applies for any function. Actually, we don't even need to go to differentiation. I want to solve g of x is equal to, instead of typing, I'll do it properly. Actions, algebra. I want to solve g of x is equal to 0.75. And just remembering g of x is a circular function, we've got no domain at the moment. If I try and solve that, solving for x, okay, if I solve that, I get this thing, 3.14159, so that's pi, that's CAS showing pi, and then this n2 plus blah, or x is equal to this, n2 plus blah. But what are these n2 things? Where's this coming from? Well, what this is trying to do is solve, if I go tab, 0.8. Okay, I was trying to solve g of x is equal to 0.75. So I've just put in a horizontal line here at y is equal to 0.75, and you can see circular function crosses it once, crosses it twice, crosses it 3, 4, 5, 6, 7, 8. It keeps going on. It has what's called an infinite amount of solutions. Okay? And what the CAS is giving us back, because we didn't define a domain, is telling us, well, it is equal to pi times, and this n2 is any number, 1, 2, any integer number, 1, 2, 3, 4, 5, 6, 7, and that corresponds to all these different solutions that we get. So if you ever try and do a solve, or you're dealing with circular functions in particular, and you get this n2 thing popping up, or an n, random bold n in there, that's a dead set giveaway that you need to include a domain. Because watch what happens if I go back and to copy all that in, and I'm going to put in a domain. Next, let's just go to 8. I've defined it, and now I've defined it with a domain, and now I do the solve. Because if I go look at the graph is short, and I have 1, 2, 3, 4, 5, 6 solutions. Since there's what's called a discrete amount of solutions, a set amount of them, it doesn't keep going on and on forever. The CAS is now actually going to list them, and it's listed all 6 solutions for that domain. So, big takeaway point from this couple of lines of code is if you see this N2 or a big bold N somewhere in your solution, that's a giveaway that you need to make a domain for your original function. Right. Differentiation. Let's have a look at the commands we can do there. Differentiation comes under the broader topic of calculus. Ooh, that's not what I wanted to do. Menu, calculus. And we have derivative, integral, and function min, function max. What you're probably going to want to, you'll be using derivative, certainly. You may use integral, but all the integrals we do at year 11 level, we could just use the polynomial shortcut. Function min, function max, probably certainly use. And then tangent line and normal line are super handy to know that they exist. Because not only it saves you having to break down a problem, then instead of finding the derivative of a function, then finding what that derivative is at a certain coordinate, then using that as the gradient to then find the equation of the tangent line, the CAS will do that all just in a single command. But let's have a look. Let's go derivative. We're going to do the derivative, and since we're dealing with f of x, yeah. So we had f of x was there's last time I put it in. It's quadratic, x squared plus 3x minus 5. Now that would be pretty easy for us to differentiate by hand, but it's nice to have it. What I would always suggest is going back to rule number 1 is we've done the derivative, but we're also going to define h of x as equal to and instead of me doing shortcuts, let me show you how to do this properly. What we're going to do is store the derivative as a new function called h of x. Now we can't actually type f dash and things in our CAS, but we can just use a different letter. So if we remember f of x is the original function, well, we can store the derivative of it and just call it h of x instead. So if I go menu, calculus, menu, calculus, derivative, I'm going to take the derivative with respect to x of f of x, and it's stored. Okay, so if I want to now find what is the gradient at 2, I can just go h of 2, and the gradient is 7. If I want to find the gradient at -4, so if I go h of -4, undefined, why is it undefined? Because we had a domain in our original function. Or I could go h, what's the gradient at 10, at x equals 10, 9. I can do all of those. So we can get the derivative and we can store it as a new function, which is really handy. It allows us solving a bunch of problems. Function min and function max does exactly what the name says. So let's have a look at that. Calculus, let's go function min, and we'll do g of x, and I want it to tell me the x coordinates. Now if we didn't put that in, let's just have a look at this. F min g of x, too few arguments, the functional command is missing one or more arguments. We need to tell, not only do we want to find the minimum of g of x, we need to tell it that I want the x coordinates of that. So it has told me, well, for this circular function, the minimum is at that turning point there and that turning point there, which we get. Fmax would do the exact same thing. This is also another place where you're likely to come across that bold N situation up here, where we have an infinite amount of solutions because we haven't included a domain. So if you use Fmin or Fmax and again get a big fat bold N somewhere in your solution, that's a giveaway that you need to include a domain in your function. Now, the last thing I want to show you is finding the equation of the tangent. So just as a reminder, what we're working with, let's copy that. That's f of x. Let's say the question asks you, find the tangent to that equation at x equals 3. Okay. I want to find the equation of the tangent of that equation at x equals 3. How you would normally do it by hand? Okay, well, we'd have to find the derivative. We'd then find what the derivative or the gradient is equal to at x equals 3. We would then also find the y-coordinate at x equals 3, and using the gradient and the y-coordinate, we could create an equation of the form y equals mx plus c. And that's doing it all by hand. Watch what the CAS can do. Calculus. Tangent line. I want to find the tangent of f of x when x is equal to, we said, 3. There we go, done. We just found out that the gradient is 9, therefore it's using 9x because 9 is our m value, and then it's also found out the y-intercept of that tangent line would be negative 14. So it's done all the work for us in one punch of a button. That's pretty powerful. That's about it for the CAS skills to look out for. I can't stress enough, define your function and include a domain, and get used to using your CAS. So if you haven't been doing much revision while using your CAS, get used to doing it. Be aware in the exams, don't just write the answer, write down the command that you would have used. Okay, whatever, pretty much if you're typing something in the CAS, like if you use tangent line f of x blah blah blah, x equals 3, write that down as what the command is, and that's effectively your working. That's it from me. All the best. If you have any issues, please email me.